Okay, so welcome back to another session of this CRE GATE previous year questions. So, like till last for the last two classes, we were looking into a few concepts. So we looked into how we can write the rate equations of different kinds of reactions, or the first order reaction, second order reaction, and so on. We looked into the design of reactors, the ideal reactors, batch reactor, CSTR, PFR. We looked into some special topics as well, something like an autocatalytic reaction or recycle reactors as well. And then we started solving a few problems based on the concepts that we learned. So today also we'll be continuing that. So for today's class as well, we'll look into some of the questions from previous year GATE, which uses the concept of something like an ideal reactor design, or this Arrhenius equations, the temperature dependency of rate equations, or the rate constants, and so on. So yeah, today also we'll be spending this lecture to look into some previous year questions, and let's get on with it. So regarding the concepts that we learned, if anyone has any doubt, like feel free to like reach me. You can always like email me, or like you can always interrupt me during the class and ask me to like repeat if you have any doubts regarding the concepts. And yeah, let's get on with today's session. Okay, fine. So just go through this question. So this is like a really straightforward question if you ask me. It's based on ideal reactor design. Just go through this question. I'll give you guys a minute, and let's see how we can solve this question. Okay. So yeah, in this question, reactant A decomposes to give products B and C. So the reaction is A gives B plus C in the presence of an enzyme in a well-stirred batch reactor. So it's a batch reactor that we are talking about. And the kinetic rate expression, or the rate of reaction, is given by minus Ra is equal to 0.01 Ca by 0.05 plus Ca, where Ca is the concentration of the reactant A. If the initial concentration of A is 0.02 mole per liter, then the time taken to achieve 50% conversion of A is dash minutes, rounded off to two decimal places. Right. So basically, this is just a direct question with regards to your batch reactor. So like, I hope you guys remember the equation for our batch reactor. So it's this question, basically what you have to do is just take the design equation of the batch reactor. You have been given a few data here. So you have A giving B plus C is the reaction with the reaction rate, 0.01 Ca by 0.05 plus Ca, and the initial concentration Ca0 is also given 0.02 mole per liter. The conversion is also given, which is 50%, or Xa is equal to zero point 0.5, and we just need to find the time required to achieve this conversion in a batch reactor. So just as I said, we can directly just solve this using the batch reactor design equation. So for a batch reactor, the design equation will be T batch is equal to Ca0 into integral from 0 to Xa dxa by minus Ra. So this is the basic design equation for a batch reactor. And we have a lot of these data here. So we have Ca0, and we have the rate equation for Ra. So all we have to do is substitute these values and just integrate it with the limits 0 to xa, and xa here is zero point 0.5, right? So Ca0 they have given it as 0.02. Then Ra we can substitute it as 0.01 Ca by 0.05 plus Ca. So we'll get the integral equation like this, right? So now what we have to do is, inside the integral we have the terms in with respect to Ca. What we have to do is we have to convert those terms, or the convert the reaction rate equation in terms of xa, the conversion. So T batch will be equal to 0.02 integral of 0 to zero point 0.5, 0.05 plus Ca by 0.01 Ca dxa. We can separate these two terms as well. So it will be 0.05 by 0.01 Ca dxa plus Ca by 0.01 Ca. Okay. So this Ca and Ca in the second term will get cancelled. And in the first term, as I said, we can write Ca in terms of Xa. So for a constant density system, we can write Ca is equal to Ca0 into 1 minus Xa. So that is what we'll be writing here. Yeah. So Ca is equal to Ca0 into 1 minus Xa. Substitute that and just solve for the integration. So we'll get the terms in the integral as this. And it's a straightforward integration. So we can take out the constants. So integral of 1 by xa, 1 by x will be ln x, and integral of 1 by 1 minus xa will be minus ln of 1 minus xa. So just take the integral, apply the limits, and we'll get our final term as shown here. So ln1 will be 0. So it will be 0.02 into 5 by 0.02 into minus ln 0.5 plus 50. And just doing the mathematical operation here, we'll get T batch is approximately equal to 4.46 minutes. So that means 4.46 minutes is the time required for the batch reactor to convert 50% of A into the products B and C with the reaction kinetics or the reaction rate equation as given in the question. So yeah, as I said, it's basically just in this question all you have to do is write the design equation of batch reactor, substitute all the values that you have been given, and just integrate that equation, and finally you will get the answer, right? Okay. Any doubts? Oh, sorry, one second. No, sir. Yeah. Is this fine, Riaz? Just let me know like when you're done, and we'll move. Okay. Shall we move on?
Yes, sir, I'm done.
Okay. Fine. Uh, let's move on to the next question. Okay. So yeah, just read through this question. And again, this question is also a pretty straightforward question, but you have to apply one more concept that you have learned in the previous classes. Let's see what that is, and let's see how we can solve this question. Okay. So the following homogeneous irreversible reaction involving ideal gases A gives B plus C with the reaction rate minus Ra is equal to 0.5 Ca is carried out in a steady state ideal plug flow reactor or PFR operating at isothermal and isobaric conditions. So isothermal means the temperature is constant and isobaric means the pressure is constant. The feed stream consisting of pure A enters at 2 meter per second. In order to achieve 50% conversion of A, the required length of PFR is dash meters rounded off to two decimal places. Right. So, okay. So here also, it's basically a direct application question where you have to just apply the design equation for a PFR and substitute the values that you have been given, and you can, just find the required answer as well. So one thing we need to note or the difference between the previous question and this question is that in the previous question, it was a constant volume system or a constant density system. Here, they have given that the reaction happens in a gas phase. That means gas phases are usually considered variable volume systems. So gas phase is usually considered as variable volume systems. Okay. So you have to account for your change in volume when you are dealing with gas phase reactions. And we deal with that by using the term epsilon. Okay. So given it is a gas phase reaction, that means it is a variable volume system. So we can find epsilon like this. So we take our reaction A gives B plus C and we just write down the moles of it. So 1 mole of A will give 1 mole of B and 1 mole of C. Right. So the change in volume we can accommodate it by finding the epsilon, which we can find as n by n0 by n0. I'm sorry, n minus n0 by n0. So n is the total number of moles of product that is coming out of the system minus n0. N0 is the total number of moles that is fed into the reactor. Okay, so here n is basically 1 plus 1 and that will be 2 and n0 is 1. So we can calculate epsilon as 1 plus 1 or 2 minus 1 by 1 and we'll get epsilon as 1. Okay. Now let us just write down the other data that they have given here. So what all data they have given? So the first thing is it is an ideal PFR. Yeah. So the first thing is it is an ideal PFR operating at isothermal and isobaric conditions. Then they have given V is equal to 2 meter per second, which is basically velocity with which the pure stream of A is entering the reactor. Okay. So V, this, you can see the unit is meter per second. So you should be guessing that it should be velocity. So in most of the general cases, they would be giving something like a flow rate and such. But here it is given in terms of velocity. So let's see how we can proceed with velocity. And then XA is also given as 0.5, which is the conversion, and the reactant rate equation is 0.5 CA. Okay, so here this CA in the constant density system or constant volume system, CA was nothing but CA0 into 1 minus XA. Here, since the volume is changing or it is a variable volume system, CA will be equal to CA0 into 1 minus XA by 1 plus epsilon A XA. And since epsilon is 1 here, it will be CA0 into 1 minus XA by 1 plus XA. Got it? So let's say if the epsilon here was something like 0.5, then it would have been CA0 into 1 minus XA by 1 plus 0.5 XA, right? So since the epsilon is 1, we get our rate equation in this form. Now what we have to find here is the length of the PFR required to achieve this conversion with the velocity rate that they have given. Okay. So as I said, we can directly start with the design equation for PFR. So the design equation for an ideal PFR, we can write it in this following manner. Tau, which is the space-time of the PFR, is equal to V CA0 by FA0, which is equal to CA0 into integral 0 to XA dXA by minus RA. So this is the general equation for PFR, where V here is the volume of the PFR. So V volume is basically area into length, right? So let's say you have a PFR like this, which is usually cylindrical. So the volume will be the cross-section area of the cylinder into length of the cylinder, right? So V will be equal to A into L. So that is one thing. Then the second thing, FA0, which is basically the initial molar flow rate, will be the product of volumetric flow rate nu0 and initial concentration Ca0. So that is Fa0 will be equal to nu0 into Ca0, where Fa0 is the flow rate or the initial flow rate in molar terms, nu0 is the volumetric flow rate, and Ca0 is the initial concentration. Now, this volumetric flow rate can be written in a different form as well. So, volumetric flow rate is the product of the flow area, which is the cross-sectional area here, into velocity. Alright. So, here the cross-section area, so nu0 is equal to area into velocity, and it is into Ca0. So that means Fa0 is equal to A into V into Ca0, where the small v is the velocity and A is the flow area or the cross-sectional area. Now we just have to substitute these terms, the new forms of these terms in the design equation. So we'll substitute for V, Fa0, Xa and minus Ra in the design equation for PFR. So V will be AL into Ca0 by Fa0, which will be AVCA0, is equal to Ca0 into 0 to 0.5 dxa by minus Ra, and that Ra will be 0.5 Ca0 into 1 minus Xa by 1 plus Xa. So all the Ca0, Ch0 terms will get cancelled and A will also get cancelled. Then we'll get L by V is equal to 0 to 0.5 integral of 1 by 0.5 into 1 plus Xa by 1 minus Xa into dxa. Now just rearrange this and solve for this integral. So we just take the V to the right hand side and take out the constant 1 by 0.5 outside, and we'll get the equation like this. Now all we have to do is substitute the value for velocity V and just do this integral and apply the limits, and we'll find the final answer L. So substituting V is equal to 2 meter per second and integrating this, so L will be 2 by 0.5, 0 to 0.5 integral of 1 plus Xa by 1 minus Xa dxa. This integral, what we can do is we can split this integral. Okay, so this integral, how we get this term is that by splitting this integral term. So 1 plus Xa by 1 minus Xa can be splitted into two terms, 1 by 1 minus Xa plus Xa by 1 minus Xa. Or there is another method of doing this as well, like the standard textbooks usually try to make both the numerator and denominator same by some mathematical manipulations. So what we'll try to do is we'll add and subtract Xa to the numerator. Okay, so the numerator will become 1 plus Xa plus Xa minus Xa, and we'll then split this term. So one of the terms will become something like 1 minus Xa by 1 minus Xa, and it will get cancelled, and the remaining term will be 2Xa by 1 minus Xa kind of term. So you can refer your mathematics notes to like see how we can do this integration here. And the final integration, after the integration, we'll get the integral term as minus 2 ln 1 minus Xa minus Xa from 0 to 0.5. And now we just have to apply the limits here and solve for this expression. We'll get the final value for L. So now applying these limits 0.5 and 0. So the 0 limit will become 0, and just find the value for this expression, and we'll get the final answer L as 3.54 meters. So the right answer according to the keys vary between 3.49 to 3.61 meters. right? So again, what we did here is basically just apply the basic design equation for PFR, just manipulate the terms of volume and Fa0 or the molar flow rate with respect to the values that we have with us. So for example, volume is basically area into length. We needed to find the length. So it is area into length, and Fa0, the molar flow rate, will be product of volumetric flow rate and Ca0, the initial concentration. And the volumetric flow rate nu 0 will be equal to cross section area A into length of the, or sorry, into velocity of the stream. And then all we have to do is substitute these values in the design equation and solve for the length L of the reactor, and we'll get the final answer as 3.54 meters. Okay, so these are like some of the straightforward questions that you can expect from CRE for gate exams. And like if anyone has any doubts regarding how we do this integration also, like just let me know, we can look at that as well. But I would suggest you you know when you learn mathematics, you will learn these how to integrate these kinds of integrations. So yeah, just is this clear? Like if you want me to do the integration, or like do you want me to repeat any of these parts in this question? Just let me know. Okay, integration, right? Fine. Okay, I'll okay, fine. One second. Just give me a moment. Let me just connect my writing device. I'll do it. Okay. Share screen. Yeah. So yeah, 1 plus xa by 1 minus xa. This will be 1 by 1 minus xa, and that also doesn't work. I did this integration. Wait. 1 plus xa by 1 minus xa into dxa. Yeah. So what we have to do here is if we take a minus sign outside here, xa plus 1, xa minus 1. Okay. Just rearrange it like this: xa plus 1 by xa minus 1, and just take the minus term outside here. Okay. Now what we can do is add or subtract this by 1. Okay. So xa plus 1 plus 1 minus 1 by xa minus 1, the whole integral. Right. So now we can rearrange this: xa minus 1 by xa minus 1 plus 2 by xa minus 1 the whole into minus 1 dxa. Okay, yeah, now this is right. And this is much more simpler as well compared to the other methods. So now, this first term, xa minus 1, xa minus 1, this will be 1. Okay, so integral 1 plus 2 by xa minus 1 dxa. Now you can see how simpler it is to like integrate. So integral 1 dxa will be xa and 2 into xa minus 1, that will be 2 into ln xa minus 1, right? So this is how you do an integration of this sort. And now if you have limits here, let's say 0 to 0.5, you just apply the limits here and we can find this equation. So yeah, so this is how you do this equation. So all we have to do is manipulate the numerator so that we can cancel one of the terms because it will become equal to the denominator, and the other term will be a simplified version of this, right? Okay. Um, yeah, so is this okay? Okay, fine. So yeah, so this is how you do the integration, and just apply the limits and you can solve for the integration and find the final answer. So is this concept clear? Is the question clear? If it's clear, like we can move on to the next one. Okay, fine. Let's move on. Okay. So this is based on the recycle reactor that we learned in the previous lectures. So just let's first read through this question. So an elementary irreversible liquid phase reaction 2A gives B is carried out under isothermal conditions in a 1 meter cube ideal plug flow reactor as shown in the figure. The volumetric flow rate of fresh A nu1 is equal to 10 meter cube per hour and its concentration Ca1 is equal to 2 kilomole per meter cube. For a recycle ratio R is equal to 0, the conversion of A at location 2 with respect to the fresh feed or location 1 is 50%, and for R is equal to infinity, the corresponding conversion of A is dash rounded off to 1 decimal place. Okay, so let's see. In this question, they have given us a PFR and it is a recycle reactor or recycle PFR. So they are recycling a part of the product back into the system, and they have given us two cases. So the first case is for recycle ratio R equal to 0. They have given us a conversion of 50%, and we need to find what is the corresponding conversion when R is infinity. Okay. So the concept that we need to use here are as follows. So the first one, we need to know the design equations for ideal reactors. So here we are using a PFR, and the other concept is with regards to recycle reactor. So one peculiar thing that we learned about recycle reactor is that when the recycle ratio is 0, the recycle reactor basically acts like an ideal PFR with no recycle. So the design equation for ideal PFR is applicable there. And when the recycle ratio is infinity, at that time a recycle reactor will basically act as an ideal CSTR. So in that case, the basic design equation for CSTR will be applicable for R is equal to infinity case. So all we have to do here is take these two cases. The first case, apply the design equation for PFR and find whatever is unknown. And in the second case, apply the design equation for CSTR and find the unknown, which is the conversion. Right. So let's see how we can proceed. So this is basically the idea of how we have to proceed for this question. Let's just start doing, and let's see how we can proceed with the data they have given us and what we need to find. Okay, fine. So given it is a recycle reactor with volume 1 meter cube, and there are two cases, R is equal to 0 with conversion 50% or 0.5, and R is infinity, and that is where we need to find the conversion. Okay. So other data they have given is that the reaction is 2A gives B, and this is a second order reaction, and the reaction rate equation can be written as RA is equal to KCA square. So in the question itself they have given that 2A is giving B. It is an elementary liquid phase irreversible reaction. So since it is liquid phase, there is no change in volume, or epsilon is 0 here, so we don't need to worry about epsilon. And it is an elementary reaction, so rate equation is basically minus RA is equal to KCA square. Okay, now what else they have given? They have given us the volumetric flow rate. Okay, before that, as I said, at R is equal to 0, this reactor will behave like an ideal PFR, and when R is at infinity, this will behave like an ideal CSTR. Okay. Okay, fine. Once again. Okay. Let us take the ideal CSTR case first. So just write the basic design equation for ideal CSTR, and that is tau is equal to V by nu 0 is equal to Ca0 minus Ca by minus Ra. So we take the volume as 1 and nu 0, which is basically the initial flow rate. They have given us 10. So 1 by 10 is equal to Ca0 minus Ca by Kca square, which is the reaction rate equation. Right. So Ca square or the Kca square, we can write it as Kca0 square into 1 minus Xa, because we can write Ca is equal to Ca0 into 1 minus Xa. So this is just some rearrangement here. So basically what happens is, Ca is equal to Ca0 into 1 minus Xa, and Ca minus, just rearrange this, Ca minus Ca0 will become minus Ca0 Xa, or Ca0 minus Ca will become Ca0 Xa. So we are trying to replace this numerator here. So yeah, we are trying to replace this numerator here with Xa term. Okay. So just rewrite the equation. 1 by 10 will be equal to Ca0 into Xa by K Ca0 square into 1 minus Xa the whole square. Okay. So now here we have Ca0. We have the value for Xa as well. The conversion is given as 50% and Ca0 is given as well. So the unknown here is K, which is the reaction rate constant. So K is unknown. Oh, sorry. This is the CSTR case, right? So for CSTR case, we don't know the conversion. We need to find the conversion, right? Yeah. So here now the thing is in this equation, we only know Ca0. We don't know Xa because that is what we need to find. And we don't know K as well, which is the reaction rate constant. So what we do is we need to find this K first, which is unknown, and then substitute this K in this equation and then find the conversion. So first we need to find K. And we can find this K by using the PFR case where R is equal to 0. Okay. Because in R is equal to 0, they have given us one more extra detail there that the conversion is 50%. So now all we need to do is write the design equation for ideal PFR and find the value for K from the design equation of PFR. And once we find the value of K from the PFR case, substitute the K here in the CSTR case, and then we can find the conversion of this ideal CSTR case. So for PFR, the design equation is as follows, which is tau is equal to V by nu 0 is equal to minus dCA by minus RA. Or we can even write this as Ca0 into integral 0 to Xa dxa by minus R. So V and nu 0 is given as 1 and 10. So 1 by 10 will be Ca0 into integral 0 to Xa, and Xa is also given for us, which is 50%. And just write the equation integral as dxa by minus Ra, and the minus Ra is K Ca0 square into 1 minus Xa the whole square. Okay. Now all we have to do is just integrate this equation with the limits 0 to Xa. Xa is 0.5. So just integrate it with from the limits 0 to 0.5, and the unknown here is only K. We can find the value for K. So substitute the values that they have given for us. Ca0 is 2, Xa is 0.5. Now just substitute it in the equation and then integrate. Yeah, so okay. So 1 by 10 will be equal to 2 into 0 to 0.5 integral dxa by K Ca0 square, which is 2 square, into 1 minus Xa the whole square. So 1 by 10 is equal to, just take out the constants and write the equation again. So it will be the K into 2 square is constant, so we can take it out and we can solve this integration of integral 0 to 0.5 dxa by 1 minus Xa the whole square. So now while solving this integration, we can even rearrange this in terms of taking the K from RHS to LHS. So the equation will become K is equal to 2 by 4 into 10 by 1 integral of 0 to 0.5 dxa by 1 minus Xa the whole square. So integral of 1 by x raised to n, or basically integral of x raised to minus n, is what we'll be doing here. So, yeah, okay. One second. Yeah, okay. Okay. So the integration here, so 1 by 1 minus xa the whole square, that will be 1 minus xa the whole raised to minus 2. So okay, what I'll do, I'll write this integration as well, like just like I did for the last question. Let's see how we'll find the answer. Okay. So here the integration is integral 1 by 1 minus xa the whole square. So this is basically integral of 1 minus xa the whole raised to minus 2. Okay. So integration of this x raised to n is basically x raised to n plus 1 by n plus 1. Okay. This is the integral of x raised to n. So you just have to apply this here also. So this will become integral of 1 minus xa the whole raised to minus 2, and this is basically 1 minus xa the whole raised to minus 2 plus 1 by minus 2 plus 1. Now one more thing is, if x is basically a function of something, you have to differentiate that function as well with respect to x. Okay, and multiply it here. So this will be equal to this 1 minus xa the whole raised to minus 2 plus 1 by minus 2 plus 1 into differential with respect to dxa of 1 minus xa the whole square. Okay. Oh, sorry. Yeah. Okay. So this will be the integration of this. So now we can write this first term, 1 minus xa the whole raised to minus 1 by minus 1 into d by dxa of 1 minus xa the whole square is basically minus 2xa, right? Now how we do this differential, I hope you guys know. So this minus 1 and minus will get cancelled, and this will basically become 2xa by 1 minus xa. So this will be integral of 1 by 1 minus xa the whole square. Okay. Is this integration clear? Like, do you guys want me to repeat this? I think like these things will be taught in mathematics, engineering mathematics, and I think you might have learned this in your high school as well during calculus. So yeah, just go through this integration, and like if you want me to repeat it, just let me know. If everything is clear, we'll just move on to the question. Fine. Okay. So that is how we did this integration here. This dxa by 1 minus xa the whole square will become, you know, we'll do this integration, we'll apply the limits, and we'll get the final answer as 5. So k will be equal to 5. Now substitute k is equal to 5 in the ideal CSTR equation. So the CSTR equation is 1 by 10 Ca0 into Xa by k Ca0 square into 1 minus Xa the whole square. We had the values for Ca0. We just found out the value for k. Now all we have is the unknown Xa. So just write this equation in terms of Xa. So we'll get this equation as 1 by 10 is equal to 2xa by 20 into 1 minus xa the whole square. Now let's simplify this equation. It will be 1 minus xa the whole square is equal to xa, and by just opening this square and rearranging this, we'll get a quadratic equation which is 1 plus 1 minus 3xa plus xa square is equal to 0. Now all we have to do is just solve this quadratic equation. So solving this quadratic equation, we'll get two solutions. So let's see how we can do it. So 1 minus 3xa plus xa square is equal to 0. So xa will be, we can get the xa as minus b plus or minus root of b square minus 4ac by 2a. So just where this a, b, c are the coefficients of xa square, xa and the constant respectively. So just solve this quadratic equation like this. So xa will be 3 plus or minus root of 3 square minus 4 by 2. So that will be 3 plus or minus root of 5 by 2. So we don't need to solve, I mean we can solve this exactly, or what we can do is we have two possibilities here. One is 3 plus root 5 by 2 and the other is 3 minus root 5 by 2. So this 3 plus root 5 by 2 is basically greater than 1. So conversion cannot be greater than 1. Okay, but the other case 3 minus root 5 by 2 will be less than 1, and that is a possible value for conversion. Okay, so we'll just have to evaluate 3 minus root 5 by 2, and when we evaluate that, we'll get a conversion value less than 1, which is a realistic value. Yeah. So just writing, taking that 3 minus root 5 by 2, we'll get the conversion as 0.382, or in terms of percentage, we'll get 38.2% as our conversion. So this is the conversion when R is tending to infinity for the recycle reactor. So just recapping this whole question. So in this question, we had a recycle reactor with two cases, R is equal to 0 and R tends to infinity. So as we learned, R is equal to 0 means it is just an ideal PFR with no recycle, and R tending to infinity means it is an ideal CSTR. So just write the design equations for these two cases, the ideal PFR and ideal CSTR. So in the ideal PFR case, we had all the data given to us except for the reaction rate constant. So we just substitute all the values that we had in the design equation for ideal PFR, and we found out the value for rate constant from ideal PFR case. Now all we have to do is go to ideal CSTR case and substitute this rate constant value in the ideal CSTR equation, and we'll get a quadratic equation in terms of XA, the conversion. And when we solve this quadratic equation, we'll get one value greater than 1 and the other value less than 1. So conversion cannot be greater than 100% or conversion cannot be greater than 1. So we'll take the value which is less than 1, and that value comes out to be 0.382, or in terms of percentage, the conversion will be 38.2 percentage. So that is how we did this question, right? So again, you can see this question basically what we are doing is we are just using the design equations for CSTR and PFR and finding the unknowns for the question. Yeah, so is this question clear to everyone? Do you want me to like repeat any part of it? Okay. Yeah, fine. So yeah, it's almost 7, right? Okay. Let us stop this point for today. So we solved 3 questions. I actually had one more question in mind, but it's a pretty lengthy question like this, so it'll take a lot of time. What we'll do is we'll spend one more class doing some previous year problems with regards to ideal reactors and rate equations, and from then on we'll see what we can do for the subsequent classes. So probably one or two more classes will be spent on solving questions related to ideal reactors and temperature dependency of rate equations like the Arrhenius theorem or the rate equations and so on. And after that, we'll look into non-ideal reactors, then Thiele modulus, and the other catalysis part of CRE. Okay. So yeah, that's it for today. If you guys have any doubts, like as I said, please do reach out to me, and I'll try my best to help you guys out. And yeah, thank you for joining, and I hope to see you all next Monday. I hope this